Alright, so today we're talking about something called the cross product. And so the cross product of a vector is the same kind of idea as our dot product, except instead of a scalar, we're going to get a vector. So our notation is A cross B, that X in the middle stands for the cross product of vectors A and B. And the calculation for A cross B, if we're looking at the magnitude, is very similar to the dot product, where the magnitude of A cross B is the magnitude of A times the magnitude of B, sine of theta, where theta is the angle in between them. However, the actual cross product isn't a scalar, isn't just a number. It's going to be a vector, and the computation can be a little bit tricky. But all of our notation is the same as before. So if we're looking at the magnitude of the cross product, it's AB sine of theta. And the angle is where they're placed tail to tail. If I look at it pictorially, what I'm really looking at is that piece there. And I multiply that times the magnitude of A. So when we did the dot product, we were able to translate that into a projection of B onto A. It's not the same idea here, and we'll see how it's different in a second. The big idea is that the cross product is a vector. It's not a scalar value, it's not a number, it produces a vector, and it has two properties. The first one is that it is perpendicular to the plane formed by vectors A and B. We also say it's normal to the plane. The direction, we'll see there's two possibilities. The direction is determined by something called the right hand rule, where we take our right hand and we are going to curl one vector onto the other, and our thumb is going to tell us which direction we're going. So let's investigate that a little bit more. We have our right hand rule. If I take two vectors, A and B, I have two possible outcomes for the cross product. So it's either a vector normal to that plane, it could go that way, or it could go down, and I don't know which one it is. And so we have this rule that allows us to determine it, called the right hand rule. So if I imagine taking two vectors A and B, if I place my right hand at the vertex, and if I imagine curling A onto B, the direction of my thumb is the direction of the cross product. So curling A onto B, my thumb points upward, so that would be the cross product of A onto B. If I looked at B and A and wanted to know B cross A, well, I'd have to turn my hand around to curl B onto A, and my cross product is going to be going the other direction. So if A and B were flat on the whiteboard, the cross product of A and B would come out towards you, perpendicular, and the cross product of BA would go back into the board away from you. Alright, the computation is a little bit tricky because we're going to deal with a matrix that you may or may not be familiar with. And so I'm going to produce a vector, and the way that we're going to do that is we have two vectors to start with, A and B, where A is 2i plus 3j plus k, and B is 4i plus j plus 2k. If I look at the cross product, and I just substitute in my vectors as we have it, and if I think about distributing that cross product between those vectors, I distribute the 2i times 4i, j, and 2k, and take the cross product of all of that. So I get 2 times 4, I cross I, 2 times 1, I cross j, 1 times 2, I cross k. And before, when our dot product we did this, we had things either go to 0 or go to 1, which was nice. It left us with a scalar value. It's not quite the same here. If I look at I cross I, those are in the same direction. They form an angle of 0 degrees. And if I use that the magnitude is the magnitude of the cross product is the product of the magnitude sine of theta. If theta is 0, the whole thing there becomes 0, which is nice. So that goes away. But I cross j is k. And we'll look at y here. So if I look at I and j, and I imagine curling I onto j, with my right hand, my thumb will be pointing upwards as k. So I cross j becomes k. I cross k, if I was to imagine curling I onto k, I would have to have my thumb pointing in the negative j direction. So that's hard to do. It's difficult to notice, and things aren't canceling. We're getting weird cross products, some positive, some negative, and so we organize this into a 3x3 matrix. So we take I, j, and k, that's our first row, and then the vector A is our second row, the vector B is our third row. And we calculate something called the determinant of this vector. And the way that we do that is I know that when I do I and I, so when I did the 2 times the 4, which is the first column of my matrix, it went away because the cross product of I in itself was 0. So what I would be left with would be the 3, 1, the 1, and the 2 of my matrix there. What that looks like here is I is really concerned with that piece of the matrix. J, and I subtract this J value, that's how I figure out my determinant, deals with everything but column J, so 2, 1, 4, 2. And then K, I add that, deals with everything but column K, 2, 3, 4, and 1. And then to figure out my process here, just like I looked at before when I did my distribution, I multiply and I subtract, which gives me 3 times 2 minus 1 times 1 minus J, 2 times 2 times 4 times 1, and K, 2 times 1 minus 4 times 3. I simplify everything down, and I get 5i minus 0j minus 10k is my cross product of those two vectors.